the cloud. Okay, so we're going to do HDL, EGL. And let me go ahead and share screen. Okay, let's go here. All right, so I've got a whole bunch of examples down here, which we're going to get to, but let's start over here. All right, so the objective, so the title of today's lecture or whatever is HGL, EGL, and that stands for the hydraulic grade line and the energy grade line. And we'll talk about that in a second. They always get mentioned together. Yes, you're a very good dog, but I can't go right now. I might be playing fetch with my dog over this. Okay. So the purpose of today is we're going to construct the hydraulic grade line and the energy grade line for various fluid systems. Okay, and then we're gonna like define, I mean, this is kind of all part of the same thing. Define and explain the physical meaning of the HCl EGL. Okay, one thing that I made a note of here, and I don't really remember why, but for some reason this needs to be known now. So we're just gonna go ahead and put this. So just like this is an aside, I guess. Okay, head loss. Okay, so remember, head loss is just you lose energy due to friction, well, or viscosity, or whatever the whatever the reason may be, in an expansion. Okay, and that is defined as head loss equals V1 minus V2 squared over 2G. Okay, so that's just something, I don't really know where that's going to show up. I just have it in my notes and I wrote it down right here. So it's important that we have that. I don't remember why. All right, so we're gonna, basically what we're gonna get to here is the reason why. So there's a few different ways you can write the Bernoulli equation. I even put that in like one of your homework assignments, was like, what does it look like if everything is written in terms of pressures, or everything is written in terms of lengths, or everything is written in terms of energies, or whatever. And right now we're going to talk a little bit about why we always think about it in terms of heads, okay? And so, or lengths, I guess. So one of the way that yes, that's fine. Okay. Okay. Can you guys still hear me? I'm sure you can, right?
Yes.
Okay, good. Okay. Okay, so I tend to think of this as like the total energy in a system. Okay, and as the total energy as being, well, let's see, TE equals P on gamma plus Z plus V squared on 2G. Okay, so you remember this from the Bernoulli equation, and we've been using it in the, in the energy equation. And this quantity right here is often just defined technically, as they'll say the EGL equals energy grade line equals. Okay, so the energy grade line is just your total of these three things. Okay, but it's not really energy, but it could be converted to energy by just like some algebraic manipulations. It's just, we're just keeping track of our three forms of energy, essentially: potential energy due to pressure, potential energy due to elevation, and potential or kinetic energy. Okay, so we're basically just keeping track of these three things. Okay, the total energy in a flow, generally, okay, it decreases in the direction of the flow. Okay, why would it decrease? Why do we lose energy in the direction of the flow?
Is it friction?
Friction, right, due to head loss. Okay, so you got friction, you're gonna lose energy. Okay, that technically you're losing the energy due to heat. It's not really a lot of heat, you know, it's not really gonna heat up your water or anything or your fluid. I guess it depends on how little fluid you have, but generally in the direction of flow, it decreases unless, what could cause the amount of energy to increase?
If it's flowing to a higher area or a higher height, it would get.
No, because, so if it goes to a higher area, then what's gonna happen is it's gonna lose pressure or it's gonna lose kinetic energy. So it's either gonna slow down or it's gonna lose pressure, probably, you know, well, I guess inside a pipe, it'll just lose pressure. But good thinking.
Could I have a pump?
Pump, yep, unless there's a pump. A pump, okay, so unless you add energy to the system from outside, it's always losing energy. Okay, and that's not just a fluids idea, that's like a general idea of all of, you know, the physical world, right? Unless you add energy to the system, it's always going to lose energy. Okay, so this is the total energy, and that's the EGL. And so what's going to happen is you're going to have some piping system, and we're going to draw the energy grade line, and it's a line that's basically describing for you how much energy you have at every location. There's another line that we like to draw, and that's the HGL. And the HGL is just a piezometric head. Okay, so we don't use that term as often as I would like, but the piezometric head, okay, and that's P on gamma plus Z. Okay, so that's just the potential energy of the system. And that's the HGL. Okay, I'm gonna go ahead and erase the word piezometric head. I'm gonna write HGL. Okay, the hydraulic grade line. Okay, and so now I'm going to kind of give you an idea of what all of this is. Okay, and one of the keys to remember all this is these are all measured in units of length. Okay, so it could be meters or feet or inches or, you know, whatever, but it's not, you know, P on gamma is a length, Z is a length, V squared on 2G is a length. And it really makes plotting these things really nice. So one of the typical ways that we do this is we imagine we've got a pipe. Actually, I say that, I don't know if this is a typical way that people do this. I know this is the way that I like to think about it. Okay, we've got a pipe. All right, now one of the things we're going to do here, I'm going to put a pipe right here. I'm going to put a little piezometers right here. Okay, so I'm just going to consider this system, right? And so I've got a pipe going right here, and let's say I've got, I don't know, I've got like a little pressure right there, and I've got a little pressure right here. Okay, great. Let's just take some points here. So I'm going to draw. Okay, so the first thing that I need to know is I'm going to keep track of these three quantities. Okay, so the Z in the system, well, in order to know Z, we need a datum. So, you know, I should be doing this with a ruler. It'll make my drawings much better. So let's go ahead and do a ruler. Plus, like I noticed in the videos that it makes a really cool noise. So here's my datum. If I decide this is my datum, and I'm curious about, say, a location right here, and this is Z, right? Z is easy to figure out. That's Z. Suppose I'm looking for a point right here. This is Z. Okay. Now I want, okay, so Z is the easiest one. Okay, now I want P on gamma. Okay, well, P on gamma, well, we could use hydrostatics and we could do some manometer rules here if we wanted to, but it's easier to just remember this. This is P on gamma. Okay. If we wanted to do manometer rules for that, well, we could say, okay, well, let's see here. So this distance right here, here up to there, if we call that H, right? We can say, okay, well, I'm going to start here. Got P atmosphere, All right, I'm going to do a manometer rule. So I'm going to add as I go down gamma times H. And that's going to give me the pressure at this point equals the pressure at just the pressure at that point. Well, if we make this gauge, it goes away. And then I end up with H equals P on gamma. Okay, so this height right here is P on gamma. Okay, does that make sense?
Yes.
Okay, I'm hopeful that this sort of, you know, the manometers now are becoming like second nature. Okay, hopefully. Lord knows we do enough of them in this class. They show up again and again and again. You guys as a class have done better on manometers than I think I've ever seen in my classes. So you're to be congratulated on that. It fires me up. Okay. So anyway, so here's P on gamma. Okay. Now, the next thing I need is V squared on 2G. Now, I don't know what V squared on 2G is for this problem. There's no real way to, like, I would have to like just make something up, and we will. And so what typically happens is, if you guys remember, we talked a little bit about, so I'm going to draw, what do they call those? A pitot tube. I'm going to put it out here only because the P on gamma is in the way. But if I imagine I've got an opening right here. Okay, so if we're doing this in class, I have a nice, what do you call it of this? But anyway, so this is now going to raise, it's going to be above. So this is where P on gamma is. This is where P on gamma is. It's going to be above that by a certain amount. And that amount that it's above it is V squared on 2G. Okay, so maybe it's like, maybe that pushes the water up to, pushes it up to here. Okay, and so what I know about V squared on 2G in this case of this pipe pipe has the same diameter all the way through. So because of that, I know it has the same V squared on 2G over here. So maybe that jumps it to about right there. Okay, so now I've got this distance right here. That's V squared on 2G. This distance right here, that's V squared on 2G. Okay. All right, so now what this means is, in terms of HGL and EGL, is, let's see here, let's do blue for total energy, red for total energy. Okay, is that total energy is Z plus P on gamma plus V squared on 2G. So that puts us like right in, I guess, well, ideally you would have these at the same spot, but anyway, like that. Well, I guess technically it's defined right here because that's the point. Okay, so let's just, a sloppy drawing. Anyway, give me 1 second. I got to fix this drawing. This is, why does it keep giving me the wrong eraser? All right, so what I'm going to do basically is I'm just going to slide this over. So it's going to come in right here and it's going to go up this way. That's our V squared on 2G. Do the same thing over here. I think you get the point, but I didn't want these to be at different locations because that kind of screws everything up. Okay, so like right in there, maybe. Oh no, it was right there. Okay, sorry about that. Okay, so that was red, I believe. Okay, so we're like right in here. All right, so this is the EGL right here, okay, because that's the sum of the Z, the P on gamma, and the V squared on 2G. This is the EGL right here. Okay, and if we assume, as is generally a pretty fair assumption, that you know, we're kind of losing that energy in a steady rate, it looks like this. Okay, so that's the EGL. Okay, the HGL, okay, it looks like this, right? We're just going to connect the blue lines, okay, because it's everything except for that V squared on 2G. Okay, so this is HGL. Okay. All right. So the difference between these two is V squared on 2G, which in this case, note, I know is a constant because the diameter of this pipe is constant. So V squared on 2G has to remain the same. Notice the elevation here, the Z's, it was constant because this pipe was horizontal. So all that energy we lost in terms of head loss, or the energy that we lost going from point 1 to point 2, it had to come out in the pressure, right? So we lost energy, and really it was in the pressure. Okay. How much energy do we lose? Well, the easy way to get at that is to draw a line perpendicular, horizontal, like this. Okay. And this right here, this is the head loss. Okay. And so right here, that is the head loss. That's the amount of energy that we lost. Okay, so this drawing, this is the easiest this would ever get. It'll almost never be this easy. Okay, and I'm going to draw you just kind of like a slightly more complicated version. And it's a pipe. I can't remember how I do this pipe, but it doesn't really matter. Okay, let's suppose we got a pipe that looks like this. It's gradually getting larger. It's going from a point over here to a point over here. Okay. So, well, all right, let's see what we got here. Okay, here's the datum. Okay, here's Z. Z, Z. Okay. Now, the pressure. Okay, well, okay, I don't really know, like, I'm kind of making up ideas here. One thing that I know is that I'm going to lose energy in the system, right? So know the EGL, wherever that is. Let's suppose it's like, I don't know, let's suppose it starts right here and it goes to some point right here. Okay, I know that I'm going to be losing energy. So EGL has to go down. It has to go down. Okay. And technically, that line would actually be concave up, and we'll deal with that later. Let's not deal with that just yet. Okay. The pressure down here. Oh wait. So the other thing that we know is that, sorry, I always work from the top down. So this is my EGL. Okay. Now this is a closed pipe. Okay. So the velocity down here, the velocity head is going to be really low. Low V squared because it's a rather large pipe. Okay, so if V squared is going to be low, then that means this distance down to here, this is V squared on 2G down to the HGL. So what I'm going to do is that means that EGL, so these things are going to be relatively close to each other here and relatively farther away over here. So maybe like right here. So this is going to look like, oops, imagine I put a little curve in there. But, not too much curve. What I care mostly is that you guys get well, we'll talk about the concavity later. Okay, so this is your HGL. Okay, the difference between those two and the way that you figure that out is by doing V squared on 2G. Okay, notice it's slow moving over here. So that means this is small. It's fast moving over here. So that means V squared on 2G is large. Okay, so what does that leave in the middle? Pressure. Here's our P on gamma. Okay, and obviously, it could be right here. So now we've got our three things that add up. Here's our HGL, which is Z plus P on gamma. Okay, and then the EGL is everything. Z plus P on gamma plus V squared on 2G. Okay, and that's how we figured this out. Now, what I want to note that I think is kind of interesting about this is a few things. So like, here's our Z down here. Okay, note that if I were to move directly upwards in this flow, like let's suppose I was right here. Well, my Z would increase some, and my P on gamma would decrease. Okay, I would have the same amount of energy. It's just that it would be in elevation instead of pressure. Right, and this V squared on 2G in those 2 points is the same, right? This is still the same V squared on 2G between those 2 locations. Okay, so moving vertical doesn't really affect it. You know, Rocky, shh, we don't need growling. Growling is for mean dogs. Hey, stop. Okay, so so that's the idea behind these things. Yeah, so when you have to draw these, so today we're just going to look at a bunch of pictures, but when you draw these, what I recommend is draw the EGL. Okay, and usually that's pretty easy, right? Because basically it's just going to slowly drop. Okay, give yourself enough room to draw underneath it, but it's just going to slowly drop. Okay, unless there's a minor loss, and we'll talk about that in 1 second. Unless there's a minor loss or a turbine, in which case it will drop fast, like in a discrete step. And then you draw HGL, okay, by just imagining or calculating, depending on the problem, V squared on 2G. Okay, last, draw Z. Once you've got those 3, then you've got everything in the whole problem, everywhere, which is pretty cool. Okay, so let me, today we're just gonna look at a bunch of pictures. I think next class, can we do all of that in one class? Probably not, but we'll talk about that. All right, so let's go down here. These are from a different textbook, a textbook I used to teach out of. Okay, and all right. Oh wait, first let me start with one thing real quick. If you have a reservoir in your problem, so if at the beginning of your problem you've got a reservoir, okay, if anywhere in there you have a reservoir, okay, I don't care if your point is here or here or here or here, right? V squared on 2G equals 0. Okay, which means if V squared on 2G equals 0, then and V squared on 2G is the difference between the total energy for the energy grade line and the HGL. So this means the EGL equals the HGL. Okay, which means if I draw a datum down here, then let's see, then this is Z for this point. This is Z for this point. This is Z for this point, and this is Z for this point, right? Easy enough. And that also means that this is P on gamma, this is P on gamma, this is P on gamma for that point, and this is P on gamma for this point. Okay, it doesn't matter, right? They all add up to the same thing. But what's interesting here, of course, is that, look, you're higher in the fluid, so you have a lower pressure. Okay, which is kind of what we would expect. Okay, so in this case, the HGL and the EGL both are right along the surface of the fluid. Huh? So let's go over here and let's start talking about what that means. All right, so HGL and EGL. And please interrupt me because this is complicated enough. So what we're going to do is, I guess we should just be kind of standard here. Let's make the EGL in red. EGL's in red. So I'm going to draw the EGL first. And I want you to kind of follow along with me and make sure that this makes sense. All right, EGL is right here. Okay, now the fluid starts to move. Right? I don't lose any energy due to friction or anything, or head losses until the fluid starts to move. Okay, technically it starts to move a little bit before this entrance. If I didn't create this drawing, I would have actually, if I had created this drawing, I would have made it kind of start to dip down right here. But, whatever. I'm not going to get that worried about that. We're just going to kind of follow along with the way the books do it. Okay. So you get to this opening and now your flow is moving. So because your flow is moving, you're going to start to lose energy. And you're going to lose energy. Well, there's nothing different about the pipe here versus here versus here versus here versus here. So you're going to lose energy at a steady rate. Okay. And so we're just going to start dropping. Okay. Now the question is, how do we know where to end up over here? Like, you know, like why did they draw it with that slope? Why didn't they draw it with a slope like, I don't know, like this, or slope like this? Because it can go negative. Okay, and we'll talk about that in a little bit. But how did they know what to do? And so what they did is they went down to this end point and they said, well, where are we going to end up? Well, this thing is exiting to the atmosphere. Okay, so if we consider these things, P on gamma, Z, and V squared on 2G. Okay, when it's exiting into the atmosphere, this thing goes away. Okay, we still have a Z. In fact, let's go ahead and draw that in here. Okay, they've already created the datum for me, so we'll just go ahead and use that. And then we've just got this V squared on 2G above that. So V squared on 2G, this has to be positive because it's a V squared on 2G. So they just said, well, you know, we're just going to use, you know, this is going to be V squared on 2G. And that's the spot we're going to aim for. Okay, when we draw this line. Okay, so, you know, what is V squared on 2G? Well, like if I asked you to draw this and I gave you no other information, as long as you ended up above this line, you know, above this location, why is this not drawing for me right now? As long as you ended up above that location, I would have to accept it. Okay, because I didn't give you any information. This line right here would be totally wrong. Okay, but this line that I'm erasing now would be fine. You know, that line would be fine. I can't quibble if there's no information. So basically we're going to lose energy and we're aiming for a spot V squared over 2 on 2G above that NZ. Okay, now, like I said, as long as you're above that NZ and I don't give you any information, well, then I have to accept it, right? Okay, so now, okay, this V squared on 2G, okay, so that's how you draw the energy grade line. Okay, now a few things, yeah, that's fine. Okay, so you'll note the head loss in this case is really huge, right? We lose a ton of energy due to head loss. And I'll explain that in a sec. Well, I'll explain that right now. Okay, before we get to the, what do you call it? Is that if we did not lose that much energy, right? Like, it's like, why do we have to lose that much energy? Well, what happens is this, your head loss, the amount of energy that you lose, so head loss is a function of this. Okay, so the faster you go, the more energy you lose. So if you didn't lose a lot of energy, let's imagine you lost very little energy in this problem. And so you ended up in a location like this. Like when you exited, you just had this insane amount, the surplus of energy. Okay. Let's see, what would that mean exactly? Oh, well, I guess it would mean V squared on 2G would be really, 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 really high, right? And so because it would be so high, what would happen is your head loss would get larger, would increase. Okay, it would increase. Okay, and it would just take some of that energy away, and it would just kind of keep eating away at it until that line, till eventually you were losing all that energy because you'd just be going too fast. Okay, so basically, you know, we don't deal with unsteady flows in here, but like probably right when they opened this thing, maybe not. I don't know, it's hard to imagine, but anyway, if for some reason the V squared on 2G was too high, then what would happen is the friction would slow it down and it would kind of go back to this position right here. Okay, so that's just, you know, just something to consider. Okay, so I'm going to erase all that because I want the EGL, the HDL to be in blue. Okay, so all right, so now to draw the HDL, all I need to ask myself is what is V squared on 2G to get at HDL? Okay, And so what I'm gonna do is I'm gonna go down here and I'm gonna look at this pipe and I'm gonna notice, oh, look, it's got a constant, diameter. So if we have a constant diameter pipe and there's only one pipe, then V squared on 2G is constant. Okay. So then that means, well, now I've actually already set this up. I have no choice in the matter. Let's see, I can't erase that. Okay, well, anyway, so if I look down here, for example, I defined V squared on 2G as being this distance. Of course, you know, the computer or whoever created these, it kind of already defined that for me, but it's the same V squared on 2G here as it is right here, as it is right here, as it is everywhere along that pipe. Okay, there's no way around it. Okay, so that means to draw my HGL, all I need to do is just, you know, is just kind of, okay, you really, this thing's really annoying today. I don't know why. Okay, anyway, so you're just going to draw this line with that constant V squared on 2G. Okay, now what's going on right here? Like what happens there? Well, what's happening is that V squared on 2G is ramping up. Okay, it's going from 0 velocity to whatever the velocity is in the, you know, in the pipe down here. Okay, I don't particularly need you to draw this little bit. Usually when I draw this, I just draw it like, I'll just have this go in like this and then just draw a little drop off like that. Okay. Technically, and they don't draw it in this picture either, but technically there is a head loss right here, which we're going to call H with a lowercase l. There's a head loss right here, which means you lose a certain amount of energy because basically the flow conditions are changing. So anywhere where there's something, in this case, an entrance, there will be a head loss, and that's what we call a minor loss. And we'll talk about those as we go. But in these drawings, they never draw an entrance loss. I will ask for you to show me the entrance loss. So what you'll do for the entrance loss is it'll look like this. This is your EGL. And you'll be like, oh, there's a head loss right here. Boom, there's a head loss. And now just draw it as before. Okay, so this is a head loss. Okay, it's just an acknowledge. I want you to acknowledge, I know that there was some kind of changing in the piping system. Something happened. If something happens, there's a head loss. Again, it could be anything. You could change from one type of pipe to another. You could have a fitting, you could have a valve, you know, whatever. And we'll talk about all those things as we go through today. Okay. Here, this is what happens if you have a pump. Okay. Oh, wait. Any questions on this?
No, sir.
Okay, cool. All right. Let's see this one. All right, so we've got a pump in your system. So this is one of the ways that they'll draw a pump. And again, your energy grade line, we're going to assume these pipes are the same. You know, so you're going to have this like constant loss of energy. Boom. Now, how do I know it's a constant loss of energy? Okay, well, there's two ways I know. One, V squared on 2G is constant. It has to be, because this diameter of pipe and this diameter of pipe are the same. Okay, any other way to, like, if one of the velocities was higher or lower than the other, it would create, it would break the conservation, it would break continuity, law of conservation of matter. Okay, staring at the drawing now, and it suddenly doesn't look like they're the same, but let's assume they're the same. The other thing that we know is that if they're the same pipe, is that the friction on the sides is the same. Okay, so like this, so if this one's made of concrete and this one's made of concrete, okay, and they have the same velocity moving through them, then they're going to lose energy at the same rate. Okay, now that won't be the case if this one were made of glass, for example, because then all of a sudden you've got a much smoother surface. It's gonna be less frictional, and it's gonna just, you know, you're gonna be very happy. All right, so here's my EGL. So what happens is we hit the pump, and what I want you to think about when we hit pumps is I want you to think, okay, that means that basically I'm just adding energy. Okay, so this EGL. Okay, don't worry about the HGL. Don't ever worry about the HGL until you've drawn the EGL. Okay, that's going to be the rule. I should just say that 50 times a day. Don't worry about the HGL until you've drawn the EGL. So here's the EGL, it bumps up, right? So usually what you'll do on your diagram is you'll label that HP. Okay, so if the pump adds 50 feet of head, then HP is 50 feet and this line goes up by 50 feet. Okay, and then of course, we're gonna start losing energy again because we're just flowing along a pipe. Same diameter pipe, it's made of the same stuff. Okay, and we'll talk about how to figure out exactly how much it loses. We'll get there. Okay, then once you've done that, then you do the HGL. Okay, so HGL. Well, V squared on 2G is constant. Okay, so once you have the EGL, all you have to do is mentally subtract the V squared on 2G. Okay, if you try to draw the HGL and the EGL at the same time, I mean, you can do it, but I just don't see why you would do it. I did that for many years. I even started teaching this class that way. And then I realized, whoa, if you have the EGL, the HGL, it gives itself to you. These are all the same number. It has to be. It's the same distance because it's the same, because it's a constant diameter pipe. Okay, so then all we need to do is draw a line that is the same distance away from the EGL the whole way. Okay. And that's what we're going to do. You are really awful. All right, so there you go. All right, so that's our HGL. Okay, now what does this tell us? It tells us some like really cool stuff, okay, that I find very interesting because it's surprising to me. Okay, V squared on 2G is constant. So that's a surprise because normally when you think of a pump, you think like, oh, well, the water or the fluid is going to be like coming out much faster than it went in. But unfortunately, that's not the case. It can't do that. There's nowhere for the water to go. But what it does instead is notice, so if I draw a datum, here's my datum. Okay, my elevation is relatively constant before and after the pipe. It does look like the exit pipe is a little bit higher. Okay, so this is my Z. And then my P on gamma. Okay, notice my P on gamma, my pressure was decreasing all along the pipe. Okay, this is my lowest pressure right here. And then all of a sudden we get the pump and boom, my pressure goes through the roof. Okay, so what the pump often does is it really just increases the pressure. Okay, so your max pressure in this drawing is right here. It's just on this side of the pipe. So this is P on gamma max. Okay, noting that right here, this is P on gamma min. That is often the case. And in fact, usually this is like a big problem, not a big problem, but a big concern when creating these systems is that a lot of times you want to put the pump, or you need to make sure that where you put the pump is before the water, the fluid cavitates. Okay, so often right before the pump, this is where cavitation is a risk. Okay, and it's a risk because the P on gamma is a minimum. Now, in this case, the P on gamma is always positive, so we're not really going to worry about that. But if the P on gamma goes negative, well, then you should check. It's still probably not going to cavitate unless it goes really negative, but something to consider. Okay, you don't want cavitation; it will screw up your pump. Okay, so don't let cavitation in. Okay, so let's go over here. We'll do another one. Oh, here we go. All right, we've got two reservoirs.
Can I ask you something?
You always can.
I just know, I know you're kind of in a flow. So I wanted to ask you, I was thinking in my head in a practical way about, basically this is in layman's terms, as layman as I can make it.
Okay.
If a certain amount of water goes into a pump and that pump is like we looked at that diagram, right? It's got a quote unquote continuous flow. The pump runs at a certain RPM because it has a motor in it. So when we're thinking about pressure and power and all those things, and you said that a pump adds energy, is that the entire point of a pump is to either lower the energy or to only increase the energy?
Only increase the energy.
Okay.
If you want to decrease the energy, well, if you only want to decrease the energy, I would think that you would just put in a reservoir somewhere in the middle. And what will happen is that'll suck all the kinetic energy out of your system through a head loss. Usually instead, what would be better if you want to lose energy is put in a turbine, and then you can actually collect the energy that you remove. Okay,
Okay,
and that's so really a pump and a turbine are like flip sides of the same thing, right?
right.
You know, I'm really flagging right now. I need some water. Hold on. I'm getting sick or something. Whew. All right. You know, it's really strange, you know, like, you know, as I get older, like, you know, my back will start hurting and like painful. I need to stretch. And then 3 days later I get sick. And I'm like, I wonder if that's connected. It's gotta be.
Probably. I appreciate you answering the question. I was curious, like, as we were discussing head loss and pressure and, you know, flow rate and all of those things, how a pump practically fits into those kinds of things, not just the numbers, but like you were saying, you can use the terms that we are learning about in a practical way to explain why we even have a pump or don't have one.
Yep.
So I
Yep.
appreciate it.
Yeah, and so what will happen in general? So a lot of times it's kind of like, well, what about this v squared on 2g? Like, how is it the pump doesn't affect that? And what it does actually is it does affect the v squared on 2g, but it doesn't change the fact that the v squared on 2g is constant. So if you have a pump, then you have more total energy, which means you can flow through this pipe faster everywhere. Okay. And so that's the thing. It'll make a higher velocity flow, but it's not going to change the fact that the velocity here and the velocity here have to be the same if those pipes have the same diameter. So,
Right. That's cool. I appreciate it.
okay. So let's go over here. No, I mean, this is why we're discussing, right? This is important stuff. Okay. This is like the whole point of this class. I mean, this is just the intro class. When you guys take, what's the next one? Hydraulics. They're going to get a lot more into these sorts of things, and they're really going to get into the systems. This kind of class is kind of like, it's kind of more sciencey. It's more theoretical, which I like better anyway, because I think, to me, it's why you go to university, is to get all the theory. You'll learn all the practical stuff when you're on the job, but without the theory, you can't figure out something new. You know, if like somebody threw something else entirely different that you'd never seen, that you couldn't look up in a book, you know, well, you can't figure that out if you don't know the theory. So, you know, you need both. Anyway, okay, so here we go, HDL and EGL. Okay, so we're gonna start, again, rules. What did I say? Don't draw the HDL until you draw the EGL, or something along those lines. I need to come up with like a song or something. Anyway, so HDL and EGL, they're both gonna start right at the surface here because there's no velocity. Okay, now normally I would draw a little head loss right here if I were drawing this, and I would expect you to. This drawing does not have that, so we can't do that. Okay, so now we're going to draw a line, and we're going to assume that this is going to lose energy as it goes from this reservoir to that reservoir. Okay, and it definitely is, right? And we notice we've got a steady pipe, we've got a constant diameter pipe. Okay, so that means that v squared on 2g is going to be constant, which means our friction, our head loss, is going to be at a constant rate. So I'll call that head loss per unit length of the pipe is going to be constant. Okay, so that means we're going to have a constant slope downwards throughout that pipe. Okay, so again, that's great, but where do we draw this thing to, right? So it's kind of like, okay, so you looked at this all made sense to you. So then you're like, okay, well, am I going to draw my line here? Am I going to draw my line here? Am I going to draw my line, you know, like here? You know, and this is the question, right? Now note, I never draw them going up. Okay, they cannot go up. Okay, that breaks all kinds of rules of thermodynamics. That would imply that there was like a continuous pump along the pipe or something. I don't know what that would mean. Okay, the HDL cannot go up unless there is a pump. Okay, unless there is a pump, it cannot go up. Okay, so you know, I had that good comment earlier. It's like, you know, what could cause the energy to go up? And it was like, oh well, if the fluid goes up, that doesn't cause the HDL to go up. That causes, you know, that causes Z to go up, but something else must go down. Okay, to accommodate for that, and you still lose energy. So okay, so come on. What is wrong with this thing today? Okay, so this one is right out, if it will allow me to erase it, which apparently. All right, so now, okay. All right, so maybe I won't erase too much today since it doesn't really want to let me do that. Okay, so what we need to do at this point, I mean, this is kind of like a little bit of art, I guess, is we want to figure out what we're going to aim for. And so I'm going to start, if I'm trying to figure that out, I know it's going to slope downwards. Either of these two are basically, either of those top two question marks are basically the same, you know, whatever. This one, the third one, it actually causes us to go below the flow. And I haven't shown you one that goes below the flow yet, but we'll explain one of those in a second. It's kind of like, well, okay. You know, does it do that? I don't know. But one thing we need to remember here is that if we're looking at this thing right here is a turbine. Okay, and this was not clearly drawn on here. I will either tell you that something is a turbine or draw a T on it. That's how I do turbines. I do pumps like this, circle with a P. And for some reason it's not taking today. Maybe this is dying, I don't know. Anyway, so there is a head loss due to this turbine. And so what I'm gonna do, and what I typically do in this case, is if I don't know how to draw that line, I'm gonna work backwards, okay? And so I'll come in here and I'll go, okay, well, let's see. I know the HGL is gonna be here. I mean, the EGL is gonna be here on the back end. Okay, technically there's a head loss right here. Okay, but I'm not drawing that right now because, you know, this is kind of a weird system. I mean, this is you know, I'm just kind of following the textbook example, which they didn't want to include those. And then I'll note that this pipe, come on, is expanding. Okay, so it's really wide right here, and it's narrow right here. Okay, so where it's really wide, V squared on 2G is very slow. So I've got, come on, V squared on 2G is low. Okay, which means the rate at which I'm losing energy right there is very low. Okay, so that means this line is going to be relatively flat. Okay, relatively flat. And then it's going to kind of go like this. Okay, I'm doing this way more exaggerated than they did. Okay, we're losing energy quickly here because V squared on 2G is high. Okay, technically the slope right there where I drew high should be the same as the slope up here because it's roughly the same diameter pipe. So let me see if I can't, you know, fix that. This isn't a very good example for this particular thing because there really isn't enough room to do this right. Okay, so it's just a little, it's concave up. So what I ask you to do on your papers basically is you write, you know, concave up. Okay, so it's curving upwards. Okay, so then what you do is you just say, oh, well, I've got a turbine, so that's a head loss. And this turbine, in this case, they drew it like the turbine is like taking a tremendous amount of flow out or a tremendous amount of energy out. Okay, you could have drawn any length of line you want here, as long as you have a line. Like I've had people turn this in and they decide that the turbine is taking that much. Okay, that's just a crummy turbine, but that's okay, right? As long as you know that the turbine causes you to lose energy in the direction of the flow, I'm okay with it. Okay, you know, so that's why like these two lines right here, either one of them would have been fine as long as it matches up with the top of this turbine line. Okay, so the turbine is going to go up. Okay, and now I'm just going to trace out what they drew because we're just going to, you know, we're going to assume that I chose that particular location. I didn't choose any particular location. I'm okay with all of them. So it's okay, but you couldn't have gone negative down here this because it just can't happen. Okay, so here we go. Red. So here's my EGL. Okay, again, always draw your EGL. Don't draw your HGL until you've drawn your EGL. Okay, once you've done that, all you have to do is figure out what V squared on 2G is. Okay, we already said that it's constant because we have a constant pipe, constant diameter pipe. So then, well, at least for the pipe section. So then the HGL then is going to always be, you know, equidistant below that. And again, you're just kind of making an artistic decision about how far below. Okay, you could have drawn it there if you'd wanted to. And you know, I usually do this, but you could have drawn it down here if you like. You could have been like, you know what? I want a little bit more space. That's fine. There's no information here. There's no way for us to know exactly where to draw that. What's key is that these two distances, that this keep the same distance all along. That's all that matters to me. Okay, if you get that, then I'm good. I'm gonna go ahead and erase that now. Okay, because you know we're just gonna kind of keep with the book solution here. Yeah. Okay. So then we got to go down here. Okay, and notice now this is a little bit more complicated, right? So notice right here, it's really slow. So v squared on 2g is small. So that means the HGL and EGL are going to be very close together. Okay, and that's why right here they're very close together. And right here, they should be about as far apart as they were up here because that pipe is about the same diameter. So this is going to kind of be like that. Okay. Now the interesting thing here is this. Well, there's a few interesting things that I like to think about with this. I'm gonna, oh, come on. Okay, so once we've done that, any questions on that? Okay, I'm assuming you guys were thinking about those lines and kind of trying to figure them out while we were, you know, kind of while I was working. But notice, like as you move along the flow, Z, you're losing elevation. So you're losing this form of potential energy, but you're gaining pressure. Okay, you're gaining this. You're gaining pressure head. Okay, you're losing elevation head. And that's kind of happening directly because of each other. Now you're still losing the total of those two, you're losing, you know, because this is constant. So all told, the sum of these two is like if you add these two up together, you're losing. So you're not gaining as much pressure as you are losing elevation, right? But you know, and you're gaining pressure because you're moving downward in the fluid. Okay, so it's just hydrostatics all over, except it's not static. Okay, the thing to think about here with this turbine is you're stealing as much energy as you can. So you've got a really large turbine, or you're taking as much head as you can. If your turbine took less head, like let's suppose you only went up to here. Let's suppose like when you're drawing that vertical line, you stopped like right in here. Okay, well, that's fine, right? Well, what would have happened then is your energy grade line would have looked like this. Okay, this is the alternate energy grade line. Right? And what would have been going on is you would have had a faster flow. Okay, and you would have had a faster flow because like there would just been more energy to use. And so you'd have had a faster flow. So V squared on 2G would have been bigger. Okay, so that's another possibility. Now there's no reason to have that happen. Okay, so it's just kind of like things that you might want to play with. Okay, so if you're designing your system, you're going to play with how much how much HT you take. I will note that if you remember that the power that you get from a turbine, the power that you remove from the system looks like this. Okay, so there is a trade-off here. Like if your HT is this right here, H sub T, okay, then H sub T is relatively small. However, by leaving energy for the fluid to flow and getting a larger V squared on 2G, you're going to get a larger Q. Okay, so it's a trade-off. Okay, I would solve this personally with a little calculus, but I think there's a lot of curves that most engineers use, and they just kind of stare at it like a turbine curve or a pump curve to figure out how to optimize that. But you know, I'm a calculus guy, so I would use calculus, but we will not be talking about how to optimize that in this class. I think I asked it one time as a bonus question and nobody had any idea. But if anybody wants to talk about it, we could talk about it. All right, here we go. Oh, any questions on this one before I move on? Let's go to this one. All right. All right, this one, the HGL and EGL. Okay, what I like about this one is this one breaks all the rules of what we just saw. Okay, and what I want very clearly for you to see here is draw the EGL first. Don't mess with the HGL. It's going to confuse you until you have the EGL. Okay, so EGL, I always like to work from both sides. Okay, so from this side, my EGL is right at the surface of the water because there's no velocity. Okay, as I say, I would normally have a little head loss right here. This particular book did not want to deal with that head loss, so we will pretend that that doesn't happen. Okay, now I need to figure out where I'm going. Okay, because I know, well, this, look, it's a constant diameter pipe, constant diameter. So that means constant V squared on 2G, okay, which means constant head loss per unit length along that pipe. Okay, so that's, or that should be a capital L, shouldn't it? Head loss per unit length. Okay, so that means we have a constant slope. Great. Okay, but let's figure out where we're drawing it, right? Because, you know, okay, I'm going right here. This is where I'm heading. Okay, here's my Z. Okay, so Z is here. Okay, I know I have no pressure right there because it's exiting into the atmosphere. So that means I need to be above it some distance for V squared on 2G, right? Again, it's artistic license. I will accept whatever you draw. Okay, for V squared on 2G, it just has to be positive. Okay, so that's why we're just aiming for a point above our exit in this case. It has to be above our exit because if it's at our exit, then that means we're saying there's no velocity there, but there is velocity there. Okay, so we draw this, you know, slow, steady decrease in energy. Okay, due to head loss, due to friction along those pipes. Okay, so that's an EGL. Okay. All right, HGL. Well, we already know we've got a constant V squared on 2G. So let's just go ahead and draw a constant V squared on 2G. Okay, it's always going to be the same distance below. And we know in this case that it's going to tie into this point right here. Okay, because there's no pressure right there, right? Because it's atmospheric. So it's going to go straight down. So that kind of determines where our line goes. So it's going to go from here to there. And again, I don't really worry about this little transition thing that they drew. Okay, so here's our EGL. And so that's our HGL, excuse me, HGL. And I suppose the HGL, I mean, they drew it kind of into this, in the little free stream, in the jet. For me, as soon as it leaves the pipe, I don't care about it anymore. Okay, so this one has an interesting, a few interesting things that happen. One, and you can see what they're drawing here. So here's Z, right? And I'm going to try to not get too overboard with it, although I can get pretty excited on this one. But notice Z is going right up to here, and all of a sudden, Z is higher than the energy line. Okay. Okay, so those are all Zs. So notice that, you know, EGL equals P on gamma plus Z plus V squared on 2G. Okay. So if the EGL, let's just throw out a number here, but let's suppose the EGL was 10 and the Z was, say, 12. Well, that tells us something about P on gamma and V squared on 2G. Something has to be negative. If Z is above the energy grade line, something has to be negative. Okay, and notice V squared on 2G is always positive, right? Because it's a squared, right? So this is always positive. I mean, that could be a 2, that could be a 4, that could be a 20. Let's just say it's a 5. Okay, well, what that means is that we've got negative pressure. Okay, obviously I'm just making up numbers here, but I'm just kind of making a point. If it goes above, then we have to have negative pressure. Okay, and now how much negative pressure? Well, in some ways I did this incorrectly because I should actually be thinking in terms of HGL. Right, so as soon as, so HGL equals P on gamma plus Z. Okay, And the same sort of idea. So if Z, if Z is like 12 and the HGL is, you know, I don't know, 5 or something. Okay, then we have to have a -7 right here. Okay, we have to have negative. So as soon as the HGL, the Z drops below the HGL, we end up with negative pressure. Okay, so we're looking at a point right here, I guess. From that point right there until this point right here. Okay, notice pressure is P on gamma. Okay, if I were to like rearrange this equation here real quick. HGL HGL minus Z equals P on gamma. Okay, so P on gamma is HGL minus Z. Right. So it's the distance between Z and the HGL. So this is P on gamma. Let's do it in blue. So P on gamma here, positive, here, positive, here. Let's see, sorry, this always confuses me. Okay, negative, okay, negative, 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 negative. Okay, all along there, you've got negative pressure. Okay, so this is P on gamma. Okay, and it's negative for this whole section of the pipe. Okay, so if you were doing a test to see if there was cavitation in this system, where would you test?
The very top.
Very top. Okay, so this is the lowest pressure. Okay, so that's where you would test. And so you've seen that in some problems so far. I think I gave you one this week where it was like, you know, it was a, or maybe it was last week. There was a Bernoulli and there was like a, you know, it was a siphon, and it looked a lot like what we have right here. And what they said is, they said, well, this is going to be one of your points. This is going to be 0.2 or something, and this is going to be 0.1, and this is going to be 0.3. Okay, and the reason they care about this point is because that's where the lowest pressure is, and that's where you have to worry about things, you know, cavitating. You know, I don't think we're going to do any math today. It's going to be very exciting. Cool. All right. Oh yeah. Okay. So this one is all about showing you what happens when you have a contraction. The reverse will happen with an expansion, okay? And again, we're gonna think about, you know, the EGL first, okay? And, you know, always do the EGL first. Don't worry about the HGL until you've done the EGL. I need to come up with a catchphrase for that, but anyway. Okay, notice we've got constant diameter, okay, up until this point, okay, which means we get constant V squared on 2G, which means we get a constant head loss per unit length. Okay, so it means we're going to have a steady downward slope. How much doesn't matter as long as it's downward. Okay, again, this is all qualitative, so we can't really solve anything. Okay, at this point right here, let's see, diameter goes down, right? Which means V squared on 2G goes up, which means the head loss per unit length goes up as well, okay? However, it's going to increase exponentially, not exponentially, it's gonna curve downwards. So this is gonna go faster and faster. We're gonna have to get into the math to show you why. But this is going to need to be concave down. Okay, and that's kind of hard to draw. Concave down. Okay. At this point, this thing exits, so this is a jet. Over here, they didn't do a very good job of showing that. This is a jet exiting right here. So we're not going to, you know, so we're not going to, you know, I don't know. Anyway, so then when, you know, we'll get to this when we get to the math. Okay, so then for the EGL, well, constant V squared on 2G. So we decide on a value for the V squared on 2G, which looks like they decided that this was the distance for V squared on 2G. and they're gonna hold that until the diameter starts to change. Okay, so that's all V squared on 2G. Then what's gonna happen is, well, the diameter decreases, the V squared on 2G is gonna increase. So we're gonna start drawing larger and larger V squareds on 2G. Okay, and again, this is also needs to be concave down, and we'll describe why. Anybody know why we end up right here? How did we know that we're gonna end up right there?
Pressure is 0.
Pressure is 0. Exactly. Okay, so if I erase all this stuff, and I think about, well, what is the HGL? Okay, well, it's this is my Z, my datum, Z equals 0. So here's Z. Okay, and we know that there's no P on gamma. Okay, so we're just going to kind of keep on cruising on until we get down to there. Okay, so that's kind of how you do that one. Okay, and the whole point here is to just think about, like, what happens if we've got a contraction. Okay, and so that's all this is. And so this will be, you know, the max velocity at the exit. You know, that'll be the velocity, the V squared on 2G at the exit. Okay. Oh, another thing that I hadn't, you know, thought about, which is kind of a cool output of all this. If you puncture a hole in the side of this thing, if you just like break a hole in this, and the water squirts out, you know, like a whale or whatever. Okay, it's going to come and it's going to stop right there. Okay, it's not going to go any higher than that. Okay, if you were to puncture a hole in it and put one of these pipes going this way in it, okay, and let that water squirt up, it's going to squirt up until it gets right there and no higher. Okay, assuming there's no, assuming the energy loss due to like the entrainment of the fluid on the sides, assuming the head loss isn't too much. Okay, but that's just, you know, something else to think about. Okay, let's see what else we got. Okay, yeah, okay, good. All right, this one, I like this one because it's got pretty much everything that there is. Okay, so again, draw the energy grade line. If you draw the energy grade line first and don't think about the HGL, then you're golden. Okay, so the first thing I always like to do is I like to think about the velocities. Well, okay, let's just draw the starting point and the finishing point. We've got two reservoirs here. Boom, starting point, finishing point. All right, what else? Let's see. Okay, right here, D is large. So V squared on 2G will be small. Okay, over here, D is small. So V squared on 2G will be large. Okay, this also means, so let's see, if V squared on 2G is small or large, this means that the head loss per unit length will be small. Okay, which means we're going to have a low sloped line. And over here, the head loss per unit length will be large. Okay, so this tells us the slope of the line. This tells us the slope of the line. Okay, so again, I like to have a head loss right here. They do not necessarily like to do that, so we will ignore that. Okay, so anyway, so basically we're connecting two lines. We're connecting a shallow line and a steep line. Shallow line. And then, well, for the steep line, I want to draw the steep line right now, but okay, well, let's see. This thing, depending on how that thing curves, will determine the shape of this. I'm not too worried about you getting the shape of the EGL right here, right? Okay, but the key is, like, I know I'm going to want it to tie in right there at the surface of the water. But there's a head loss associated with the change in the pipe right here. Okay, we haven't talked about that very much. You know, I mentioned that there should be a head loss right here every time, but that this book decided not to put in. I have no idea why. There's also a head loss. These are called the minor losses associated with this contraction right here. The thing about the head loss associated with that contraction is it gets lost in this line right here. So I don't ever ask people to draw that because it's just hard to draw. But there is a head loss right here, and so that's going to be just an immediate downward loss. Okay. And so right at the beginning of this, I told you that the head loss due to an expansion, was V1 minus V2 squared on 2G. And in this case, the V2 is the velocity in this thing. So in there, it's a 0. So it's just V squared on 2G in this case. Okay, so that's why this particular head loss right here is exactly the same thing as V squared on 2G. Okay, but you know, so anyway, but what I'm really driving at is, okay, we're working backwards a little bit. We're kind of cruising along the top of that reservoir. Okay, and then we're gonna bounce back up. And now we're just gonna draw that steeper line. And we know it's steeper because we're losing energy faster because we're in a narrower pipe. Okay, which should tell you something about designing systems. If you can get a larger pipe, you're gonna lose less energy per unit length. Okay, so that's a good thing. Of course, it costs you more to get a bigger pipe. So, and they take up more space. So those are things you got to consider. Okay, so once we get the EGL, again, once you got the EGL, the HDL is just thinking about this V squared on 2G. Okay, small and large. Small over here, so these two things are really close together. Okay, and then over here, it's large. Okay, and this concavity, let's see. Yeah, it's got to be concave down. And when we get into the math, we'll talk a little bit more about why that has to be concave down. What else? Okay, so if I asked you in this system, where is the lowest pressure? Where would it be?
Surface of the water.
Yeah, I guess that's true. You could you could definitely say right here. How about between the reservoirs? Where's the lowest pressure?
Are you talking about the top of the water again, where the EGL is?
No, not between the reservoirs. So between this point right here and this point right here, where's the lowest pressure?
Just to the right of the reservoir.
Just to the right, like right here.
Maybe up there by the top.
Okay, so remember, let's draw this again real quick. Okay, so here's Z, here's our datum. So here's Z all along the whole system. Okay, more or less, obviously not a great drawing. Here's Z, here's P on gamma. And then this one's V squared on 2G. Okay, so where's P on gamma the smallest?
Other end.
Right, this end, okay? So we're losing pressure the whole way through this system. Okay, so this is where P on gamma is the smallest. Now notice, we're not worried about cavitation here because it's never going to go negative. It can't go negative, right? Because the pressure here is 0. And we're going downwards in this fluid. I guess it could go negative if that velocity went like, you know, supersonic or something. But you know, that's not really, we're not really there. So yeah, so I think that's it. If you guys want to play with these are two, I think I've given these on exams or given them in class. You know, usually if there's enough time, I'll do this kind of as a class thing, like just kind of like, you know, try to draw this on your own. But here is here's kind of a fancy drawing of these. You know, so if you want to play with that, that's, you know, you can try, you know, you can do these, you know, on your own and then come back and compare them to, you know, what we get over here. But yeah, so we are out of time. But anyway, it's one of my favorite classes, but it's also, I don't know, interesting. I never know how much is sinking in with this one. HDL and EGL, until you really get your hands dirty, they can, you know, as long as you just draw that EGL first, that's, I mean, I can't stress that enough. And there will be an HDL, EGL in the final, there always is. So anyway, if you guys have no questions, have a great weekend. If you do have questions, I would love to hear them. All right, well then you guys have a great weekend. And if you have a, you know, particular concern or question, I'll be here 3:30 to 5:30 today. All right, See y'all later. Have a good weekend.
See you.
All right, see you guys. That's why it was being wonky. Stop share.